All right, this is the 1998 AP exam, uh, section 1. This is a non-calculator portion with 28 questions. So let's see how many problems we can get through in this video. Number 1, what's the x-coordinate of the point of inflection on the graph of y is equal to 1/3 x cubed plus 5x squared plus 24? Now we're given the original function, and if we want to find the point of inflection, we have to get to our second derivative. So we find y prime, first of all, going through power rule, bring down the 3, keep the 1/3, x squared. 5x squared becomes 10x. 24 is a constant, so that will go to 0. And simplify that down to be x squared plus 10x. But we keep going because we need to find the second derivative in order to get to our point of inflection. So x squared becomes 2x, and 10x becomes 10. Once we have our second derivative, we can find our critical point by setting our second derivative equal to 0. So 2x plus 10, solve for x, we get x equals -5. Okay. And so if we plug, now just because this is -5, just because we found a critical point doesn't necessarily mean that this is a point of inflection. And so we still have to test our ordered, we have to test our points to the left and to the right. There must be a change in sign in order for this critical point to become a point of inflection. So I can plug -6 into the second derivative. That'll give me a negative value. And if I plug in a 0 or 2 or any number 2 greater than -5, I'll get a positive number. And so concave down followed by concave up, there's a change in sign, so -5 is our solution. So I made a mistake there. I should have put an answer for D instead of A. Okay, so -5. Okay, number 2. The graph of a piecewise function is shown above between -1 and +4. What's the value of the definite integral of f of x dx from -1 to 4? Now, we're not given the formula, so we're not able to find the definite integral using power rule or whatever integral rule. However, these are geometric shapes, so we can simply total the areas between the graph and the x-axis. However, with definite integral, we have to be sure that we keep track of the positives and negatives. So here we have a triangle of area 1, rectangle of area 2, triangle of area 1. This is a triangle of area 1/2, but this is below the axis, so we have to keep track of that as a negative. And then we have a square of area 1, but that's below the axis, so we have, say, -1. And then we total those values together, 1 plus 2 plus 1 minus 1/2 minus 1, and we get 3 minus 0.5, which is 2.5. Okay, number 3, definite integral of 1 over x squared dx. So we simply just have to evaluate this integral going through power rule, first theorem of calculus. However, we have to be a little bit careful here because the power rule does not work if the variable is sitting in a denominator. So we have to bring this x squared to the top before we can apply power rule. So integral of x to the -2, go through power rule, we get x to the -1 over -1. Now we can evaluate our lower and upper bound. I'm going to simplify this to be -1 over x. Then we plug in the upper bound, we get -1/2 minus, now we plug in the lower bound, which is -1. The two negatives cancel out. -1/2 plus 1 is 1/2. All right, number 4. If f is continuous between a and b, inclusive, and differentiable for the open interval between a and b, which of the following could be false? Okay, so I just drew a picture here of a potential graph where we have a continuous and differentiable. Okay, but I drew this in a way so that one of these will be more apparent as to which one could be false. So first off, this f prime of c is equal to f of b minus f of a over b minus a. This is the formula for mean value theorem. Okay. Now, the only thing that that is required for mean value theorem to hold true is that the function is continuous on the closed interval and differentiable on the open interval. And both conditions are met, so we know that MVT, mean value theorem, has to also hold true. Okay. Part B, f of prime of c is equal to 0. That means the slope is equal to 0 for some c such that c is between a and b. Now this is saying that the slope is equal to 0, which is possible, but just because the graph is continuous and differentiable, we're not going to be able to guarantee that we're going to have a point where slope is equal to 0. And that is demonstrated by this graph here where I have continuous and differentiable. There's no sharp points and there's no breaks. However, there's not any points where the slope is equal to 0. So I meant for this graph to be always increasing. Now part C and D, these hold true because as long as we have a continuous function and on the closed interval, then we're guaranteed a minimum value and a maximum value. So this is basically going to hold true because extreme value theorem is going to hold. All it takes for extreme value theorem to hold is that we have continuous function between two closed intervals, or we have a continuous function on the closed interval. We don't even need this differentiable portion for extreme value theorem to hold. Part E, we can find the definite integral of f of x as long as the function is continuous on the closed interval, and that is true. So we know for sure that B is the one that could be false. Right, number 5, the definite integral of sine of t dt from 0 to x. So this is a pretty straightforward problem where we just find the definite integral between 0 and x. So the integral of sine of t is negative cosine, and then we have our bound 0 and x. We plug in the upper bound first, so we get negative cosine of x minus, now we plug in the lower bound, negative cosine of 0. Negative cosine of 0 is just 1, and so the two negatives will cancel out, so we get negative cosine x plus 1, which is simply 1 minus cosine of x.